Finally, we have talked about the sensors, algorithms, and so on. There's a need to think about, hey, what kind of hardware architecture I should implement these in, and is the hardware architecture going to play a very, very important role? All right. So what should the hardware architecture be? Turns out, for most of these applications that we looked at, right, most of the neural networks that we looked at, the major computations that we end up doing are matrix vector multiplication or matrix-matrix multiplication. And on the right side of it, in the right corner, I show a chart which is borrowed from IBM, showing that for speech, language, and vision processing, the red bars which are shown are basically the amount of computations for the matrix multiplication. And that, it turns out, takes up most of the computations. Turns out it's very important to do such matrix vector multiplication effectively. The second thing which I'm not showing here is that today's transformers, and I should include that here, that today's transformers not only have matrix vector multiplication for some of these language models, but they also have to do a good amount of softmax calculation. And softmax requires exponential functions. So now if you want to do sigmoid, if you want to do tan hyperbolic, for all those you have to do calculation of the, you have to do the exponential calculation. So is it possible that I do also not only matrix vector multiplication, but today's application I have to do also exponential calculations, or in other words, softmax estimations? Can I do that effectively? Or in other words, can I really come up with a circuits and architecture that efficiently implement these algorithms and maybe embody the computing principles of the brain? So whatever little that we know, it's not a von Neumann architecture, and we do the computations in the memory itself. And we also know that there's something called a memory wall. Remember, we talked about the fact that I don't want to go to my memory, fetch the data, bring it to my compute unit, do the computation, and bring it back to the memory. That traffic and all this communication really is a major bottleneck in terms of both energy and latency. Can I do it? So can I do computations in memory or near memory? Can I do approximations? Turns out approximations play an important role, and I'm not going to talk too much about approximations, but we have done a good amount of work, and if you're interested, I can refer you to some of those work on approximations. It turns out that most of the neural networks are error resilient in nature, right? So maybe 10 plus 10 doesn't have to be 20. If it's 19 or if it's 21, I can still do a reasonably good job. And even if it's approximate, I can train on the hardware, which is an approximate in nature, as long as the approximation gives me energy improvement. So those are all possible, that I can train on the architecture, and such that not only I learn the data, but I also learn the hardware. That's possible. I'm not going to go into that. Stochasticity, that's also possible to actually have stochasticity in my neurons. Remember, I talked about stochastic sigmoid function. So maybe I can do that to actually have a stochastic neural network. Event-driven computation, quite important in case of spiking neural networks. And then finally, should I still end up using the devices? Like, for example, should I use CMOS circuits? Or should I use some other kinds of new non-volatile memories which can mimic the neuron and the synaptic operations better? In other words, today we are in the regime of the GPUs and the accelerators. Is it possible that I do in-memory computing, if we do some approximations and other things, or maybe use the right kind of devices to be able to actually, be closer to what the brain does? I mean, I don't expect, nowhere close to what we can, but can we be much, much better than what we do today? So to that effect, I'm going to really focus very quickly on, near and in-memory computing and neuromorphic devices or neuromimetic devices that can mimic the neurons and synaptic operations for these kind of computing. So what's the idea? Basic idea in compute-in-memory. The basic idea is that I have a standard memory, which probably you're all familiar with. I have the word lines, and in general, I activate one word line. So if it's a 6T cell, I activate one word line, and there are, at the bottom of it, these peripherals which are shown, which is going to read that, that particular word. I can do a little bit better if I turn on two word lines. You have to be careful, not in a 6T cell, because there's going to be a short, but you can do it in an 8T cell, the read word lines, and you can turn on two read word lines and do basically, AND operation, OR operations by adding a little bit to your peripheral circuitry and making it amenable for XOR operations and all. And if you add a little bit more, now you can do ADD operations. But you can also go further and say, hey, can I turn on multiple word lines? Now, if I turn on multiple word lines, the output that I'm showing in the vertical lines is going to be a matrix, a vector multiplication, and a dot product. So if I can get a dot product, then that's going to be an analog domain, and I need more complex circuitry at the bottom that I'm showing, which are basically some sort of an analog to digital converter to be able to do the computations. These can all be done in a non-volatile memory, or it can be done in SRAM-based cells, or, which I didn't talk about, I only talked about the compute-in memory, but remember I talked about the fact that exponential functions are important, okay? So is it possible that I actually can have these exponential functions in that memory itself directly? Can I put it as a truth table? In that particular case, I actually can do also computations like map tables, different kinds of things in the memory itself without going out. But I don't want to pay for it. So it has to be all done within the same memory itself without an extra cross for the memory array. What kind of devices? So these are all very, very colorful devices, as you can see, both literally and figuratively. These are all quite colorful devices. CMOS should also be there. I can use CMOS for in-memory computing too. But I just wanted to mention the fact that there are some of these devices like magnetic tunnel junctions, RRAMs, PCMs. These can potentially be quite useful for mimicking the neuron and the synaptic operations. I'm not going to go into the details of it, but just wanted to bring the fact that some of these devices can be used in some of these computations. And sometimes they can be more effective than using an CMOS circuitry. Just to give you an idea about what some of these colorful devices that I showed are, PCMs, RRAM, MTJs, and CMOS, each sort of has its own kind of pros and cons. If I look at the cell area as an example, PCMs, RRAMs for the same technology or MTJs are going to be smaller than the SRAM cells. So that's an advantage. I can put more in the memory. However, the write energy for some of these newer devices are actually quite a bit larger because these are non-volatile memories, so the write energy is quite large. I mean, MTJ is better than, for example, PCMs and RRAMs, but SRAM is still the best. And in terms of latency, the same thing is true also, that latency for the SRAM cells are better than some of these other devices. Endurance, that plays an important role, and that may determine what kind of architecture that I would have. The PCMs and RRAMs do not have the kind of endurance that an MTJ or, for example, a CMOS circuitry would have. So now, let's try to look at matrix vector multiplication. And that's one of the major components for computing that we want to do. So now let's try to see if I can make my life simple and use basically one of those non-volatile devices. These devices are shown in terms of G11, G12. These are conductances. So each of those RRAMs and STT-M RAMs could be considered to be, and so does, for example, a CMOS circuitry could be actually a conductance. So now if I have inputs which are coming in from the left, which are V's, and then on the vertical lines, what I'm going to get is Kirchhoff's law, summation of VI times GI, VI being the input, G being the conductance. So I'm going to get a current, and current is going to be proportional to the kind of computations that I'm doing, in this particular case, dot products, right? Now, these devices can potentially be any one of those devices, PCMs, RRAMs. There's a little bit of change in architecture. We can put STT-M RAMs, ferroelectric FETs, or in fact even CMOS. A little bit more details on that architecture, the crossbar architecture. I need peripheral circuitry, and these peripheral circuitries are going to play a very, very important role. When I do matrix vector multiplication, right, when I turn on multiple word lines, I'm actually end up doing analog computing. And analog computing has its own kind of issues. So I don't want to communicate those analog values with the next set of macros for doing these kind of computations. So what I do is I convert them into the digital domain, okay? And using an analog to digital converter. Unfortunately, that's going to cost quite a lot. But one can potentially also now think of an architecture where there is going to be a bunch of these matrix vector multiplication units. I'm not showing the details of it. There'll be other circuitry around it too. Some computations, you need CPUs, small-scale CPUs to do other kinds of computations and all, and also some local memories. And this is basically a network on a chip kind of architecture. You can potentially also think of a high-density memory like a DRAM associated with. Only problem with this architecture, we'll see later on, we'll talk about it later on, is that the area is not, the array area can be quite small. But now you're going to be dominated by basically the interface circuitry for doing this analog matrix vector multiplication. If it's not an analog matrix vector multiplication, if it's a digital domain, we are turning on 2 word lines, then the interface circuitries are going to be much, much smaller. But if you really want to do these analog matrix vector multiplication, then as you can see, the area and the energy dominated by this ADCs, the high complexity ADCs. If I were to now look at basically the NOC architecture in a little more detail, they look like this. This is basically an architecture developed here at Purdue, a programmable, ultra-efficient memristor-based accelerator. It doesn't have to be memristor. It could be CMOS and other technologies where the cores basically that I'm showing at the bottom are really the cores implementing these crossbars or matrix vector multiplication. Remember that implementing such matrix vector multiplication is, if the device can implement, for example, multiple bits, you can do it in different ways. If it implements, for example, a single bit, then you need multiple crossbars to do 4-bit or 8-bit computations. And then you have to accumulate all the results. So a few things which are important. One can do weight slicing, if needed, and also bit streaming of the inputs to do basically this matrix vector multiplication so that you can, rather than having a, you still have an analog to digital converter, but now the digital to analog converter can be 1 bit if we do bit streaming. So now with that in mind, a little more details on what one can do using SIMs, the compute-in memory. So the first thing I'm going to talk about is a digital SIM. So what would be a digital SIM? So in this particular case, I'm going to turn on 2 read word lines in an 8T cell. So these are 8T cells, separate read and separate write. So if I now turn on the 2 read word lines, then one can show that what I'm going to get at the read bit line, if I p-charge the read bit line, by sensing it properly, I can do various computations. I can do XORs, I can do ANDings based on the interface circuitry that I have. Now if I do a little bit more, I can do also additions. If I add a little bit more circuitry, I can do additions. So now what one can potentially do is that using that addition, let's say, I to turn on 2 word lines, and then simultaneously if I turn on the write word line of a different row, then I can write into that cell. Since the write and the read are separated in an 8T cell, I can do that, and at the same time I can read, do the computation, and write into a different section of the memory. Only for 8T cells, because they have separate read-write ports. So I can do that, not in a 6T cell. So if I do that, effectively I'm doing in-memory computing, and I can do additions, let's say. And once I'm able to do additions, a bunch of those additions can be used for multiplication, and which is very important for my neural networks. So what would be my new architecture that looks like? The system in a compute-in-memory kind of architecture. I have the processor, and I can also think of having a sort of a compute-in-memory block. So in other words, in a conventional instruction that I normally have is basically load register R1, R2, then basically add them up in the compute unit, and then bring it back, store it back in the memory. So now all those can be replaced by one instruction that I'm showing here, which is SIM, which is compute-in-memory, in this particular case, a compute-in-memory add instruction. One can potentially think of a matrix vector multiplication or a multiplication instruction too. One can do various ways of these implementations. I talked about an 8T cell. One can do also 6T cells. In a 6T cell, remember I said that you can't turn on things simultaneously. I can't turn on two word lines simultaneously. But is it possible that I do my storing in a little bit different way, in an interleaved fashion? So in other words, what I do the storing is that I store bit 1, and then the next row basically has bit 0, the next row has bit 1, then the other row has bit 2, and so on. So I interleave the storage. If I now interleave the storage, I can potentially turn on this bit line simultaneously, right? And if I'm able to do that the way I'm showing it here, in that case you'll be able to do the compute circuitry over there, and there you can actually still use a 6T cell. If you don't want to use, for example, and that's for digital computing. Digital meaning turning on two word lines simultaneously, right? The first word line is going to be turned on. They're stored in an interleaved fashion, and that's the reason I'm able to do that. But if I want to do analog sim, then I possibly need an 8T cell. And what I'm showing here is that the read part of the 8T cell, which is basically the two transistors that I'm showing here, the 6T part is for writing or storing the values. Turns out that I can actually turn on multiple of those lines, pre-charge the bit lines, and the read bit lines, and turn on multiple of those, and depending on how much of charge is there in that line, I can determine, right, what kind of matrix vector multiplication that I've been able to do, and I can then need an analog to digital converter to basically figure out the value that I have for the dot product computation. So that's one way of doing that. So we implemented that in a 65 nanometer technology, and without going into the details of it, I basically show that this circuitry can use various things. It uses an analog to digital converter, but also remember there's a good amount of sparsity. I didn't talk much about the sparsity part of it, but it turns out that most of these computations have a good number of zeros. So if there's a good number of zeros, I can potentially skip a lot of things, and I can get rid of the complexity of the ADC. If the ADC requirement is 7 bits, maybe in a lot of cases because of sparsity I can use 5-bit ADCs. So to that effect, in this particular case, what we end up is using is a way of determining what the sparsity is, and then have a programmable ADC which can go from 2-bit to 6 bits, let's say, and do the computations. So using that, and of course having this ADC, we can do these computations, and it was implemented in a 65 nanometer technology. What I wanted to show you here is the take-home message in this particular case is that in the bottom left corner I'm showing the area breakdown and the power breakdown, and as you can see, you're dominated now by, your performance is really good, right? But you're dominated area by now these A to D converters. And these are sims for, and again, matrix vector multiplication can be used, for example, in, for any computing like, ANNs or SNNs. But SNNs in general require something else too. So what do SNNs require? Other than this matrix vector multiplication that we need to do, in fact, in reality, I don't need a matrix vector multiplication. In an SNN, I have these spikes that are coming in multiplied by the weights, so I'm going to be only doing accumulation. Okay, multiplication is not required, only doing accumulation. But then again, I can still use a crossbar to do such computations. So I can do that, but SNNs require something else. Every time I do the compute, I'll have to also update the membrane potential. Right? Every time I have to update the membrane potential. So the question, of course, is compared to the conventional hardware which doesn't do that, is it possible that a spiking hardware, I not only need in-memory computing for doing the weights, but can I have this memory also doing updates for the membrane potential? So the difference now is going to be not only doing updates for the weights, but also at the same time doing updates for the membrane potential. Can I do it in the memory itself? And that's basically, can be done, again, without going into the details of it, using a fused, WM memory and a VMEM memory together. And the architecture of it, if you're really interested, it's available in a paper called Impulse, which uses a CMOS-based IMC architecture in a 65 nanometer technology. And again, that can do, for example, the computations for SNNs. Slightly different from the standard ANN computations. Going further, you might say that if I want to do SNN processing, can I do slightly better? So far, we haven't talked about the fact that the inputs in an SNN, the timing is important, right? They can come in an asynchronous manner. If they come in an asynchronous manner, can I use that asynchronous computation by doing computations only when the spikes arrives? And if the spikes are sparse, then I don't do computation most of the time. So to that effect, there's a processor called Loihi, which is developed at Intel, that utilizes asynchronous communication to avoid computing with zero inputs, and that way they can exploit the input sparsity. In this particular case, the communication is asynchronous in nature. So the results are actually kind of interesting. They implemented keyword spotting with the Intel Loihi processor and showed about 5x reduction in dynamic energy per inference over state-of-the-art processing units, which are shown on the right side of it. So it's certainly possible to do that. Again, all these doing basically in good matrix, earlier we talked about matrix vector multiplication, and now asynchronous computing. One other thing that we need to think about is that we haven't talked any details about softmax computation, which actually turn out to be quite important when it comes to transformers and so on. So is it possible that I actually do embed transcendental functions into the memory itself? No, I don't want to pay for it in terms of area, because you can always put a ROM. Usually math tables are kept outside, right, in a DRAM. So is it possible that I keep a table in my memory itself, meaning thereby that I'm not going to have not only standard SRAM operation, RAM operation, but I'm going to also have a lookup table in there at no extra cost. Can I do that? So that's basically the idea. At no extra cost, I'm going to have a lookup table. The size of the lookup table could be, for example, 1 MB, and the RAM still is 1 MB. So at no extra cost. So I get both. Can I do that? In fact, interestingly enough, one can do that, and this is an example showing it using an RRAM array. It doesn't have to be an RRAM, it could be an, STT-MRAM array I'm showing it. It doesn't have to be STT-MRAM, it could be, for example, any computing block. In fact, it can be used in SRAMs too. The SRAMs are slightly different because they're non-volatile. I'll have to make some adjustments to it. And there was a paper that was mentioned there which talks about those adjustments that are required for SRAM cells. But again, no extra cost in terms of array area. Only a little bit of change in the peripheral circuitry. So how do we do that? This is basically showing an STT-MRAM memory. And if I want to do, for example, in the RAM mode, what I'm going to do is I turn on this word line. The difference that you see here is that instead of having one source line, I have two source lines, or rather bit lines in this particular case. One is a red one, and the other is a blue one. So if you carefully look, the cell is never connected to both the lines. It's either connected to red or blue, but not to both. So that really basically tells you the ROM storage or the table lookup storage is based on whether it's connected to the blue line or the red line. So the connection, the availability of a connection or not, basically determines a 1 or a 0, right? Now for a RAM mode, which is basically random access memory, I still need to store values. I still need to read values. So how do I do that? I turn on this word line as an example, and then I activate, in this particular case, both the red line and the blue line. So in other words, I don't have any problems reading now. When I'm reading, both the red lines and the blue lines are on, and then when I look at the source line on the left side of it, I can read the values directly, right? Read, same thing. Write, I activate it the same way as I've done, but this time I just need to make sure that both the lines are active. All right, so RAM data can be read just like that. But the next cycle, let's say, comes, and I say, hey, I want to read the ROM data. So how would I do that? Again, for the ROM data, I activate the word line, and as you might have imagined by now, I'm not going to activate both the red line and the and the blue line, I'm going to activate one, and in this particular case, I activate only, let's say, the blue line. I could have done that for the blue line too. So now what happens? For the first cell, as you can see, there's a cross, green cross shown there. That means it's not connected. That means the resistance I'm going to read is infinite. So what's the resistance I'm going to look at the middle one? The resistance I'm going to read is either RAP, the anti-parallel resistance, or the parallel resistance. So as long as I have my sense amplifier to determine whether the resistance is infinite or one of those resistance, then I'm okay, right? So my ROM read basically connection or an OR connection to the cell is what I do. So if I have a 1 MB RAM, I also have a 1 MB ROM in this particular case, or a lookup table. So I can put, for example, exponential functions and other functions in here to do the computations. How much area do I pay? In fact, there's enough space available to do my routing of these two blue lines and the red line, so the array area does not change. Only the peripheral circuitry need to change slightly my sense amplifiers now. So with that in mind, what one can do is, now one can implement this ROM, or the lookup table, which is embedded in this. In this particular case, it's an SRAM architecture. I didn't talk about the SRAM architecture. It requires a few extra functions because I don't want to write it, because in order to store the RAM data, I might have to store that RAM data into a register file, into a register. So anyway, I have an op-chip map table to do these computations versus I do these computations in, for example, this embedding of this ROM into the RAM itself. And if I do that, we do actually ROM embedded 8TS RAM, and then we can get rid of DRAM fetches altogether. No DRAM fetching. I don't have to thrash data out of my memory if needed. So a map table is replicated directly in my ROM embedded IMC macro. This macro itself can also turn on multiple word lines, as I said, right? And do, for example, the same computations that I was doing, which is matrix vector multiplication, right? So it can do MVM, it can do exponential functions and so on. So we did this for LSTM simulation. Why LSTM? Because LSTM requires that we actually do computations of the tan hyperbolic functions and sigmoid functions and so on, which is done in the memory itself. And what we found is that for this case, we actually had an improvement about 46% in speed up. So which is quite a bit compared to what otherwise would be possible. Question, of course, is so far we talked about compute in memory. They could be done in the register files, could be done in the L1 cache, L2 caches, and so on. Or in fact, you can embed a ROM in one of those caches too, as we have seen. Now, the next question is that, can I do some computations in the DRAM itself? So rather than doing computations in my L1, L2 caches, can I do it in the DRAM? And turns out, indeed, it's possible to do some of these computations in the DRAM with very slight changes. So what I'm showing here is a DRAM architecture. Yeah? And the DRAM is basically one transistor, one capacitor cell. Again, I'm not going to go into the details of it. The one capacitor, one transistor cells are stored in this DRAM array, which I'm showing here. Now, one of the interesting things is that I take basically a part of the DRAM array. If I want to do, for example, some computing in the DRAM array, what I do is that if I want to do, for example, addition, what I do is I bring those blocks that I need to do addition in the compute rows, which are shown at the bottom. So if I want to take, for example, add from A side A plus B, I take those A and B from those arrays and put it in the compute rows of the same array. I don't go anywhere else, I put it in the same array. So I repeat A, repeat B, and then I also have carry. For example, if I want to do addition, I need carry, right? And as you can see, without going into the details of it, I actually put carry and carry bar in there. So what one can do is now turn on multiple of these word lines, right? Doing A, B, and carry together. And if I turn on those, I do majority functions, and once I'm able to do the majority functions, I can do the sum operations. And again, the details of it are shown in the slide itself. I probably don't have much time left today, but what one can do is using these majority functions. Basically, once you turn on the majority function, tells you whether it's a sum function, what sum that you get. Similarly, by doing a little more computation with C and the carry and carry bar together, you can also get from carry input, you can also get the carry output. And using that, what we did is we analyzed it using a host processor, which does these computations for doing k nearest neighbor calculation. For the k nearest neighbor calculation, what we do is that we did basically the sorting, and sorting is required. So sorting is done in the host processor, and then the DRAM in this particular case actually does the Manhattan distance computation. So if I do this in this particular fashion, having the host processor do some things, and with an addition of a little bit of logic that we have done in the DRAM, what one can potentially now do is this computation both in the DRAM, in memory computing in the DRAM, and in the host processor together to be able to actually show that you can get, compared to baseline where you don't have any in-memory computing in the DRAM, compared to that, the proposed system actually has about, execution time, almost 11.7x improvement in execution time. So again, possibilities of doing in-memory computing in the DRAM is very much there. So finally, visiting for the last time, this cross-layer design from sensors, algorithms to hardware. We talked about the sensors, we talked about the algorithms, and if I now think about this hardware that does in-memory computing, what we ended up doing is we wanted to show how good or bad we are compared to, for example, state-of-the-art. So we took this algorithm, which is basically the optical flow as an example, implemented that in a GPU-based architecture like Jetson. And what we found is that for all these applications that we had, we needed frames per second to be of the order about 30 or so. But in this particular case, when we implemented that in this GPU-based baseline, this was only about 7 or 8 frames per second. In this particular case, the Jetson TX2, it's a mobile processor. Now, we also implemented that, or at least simulated that. I mean, this is a hardware implementation of this adaptive SNR sparsity-aware SIM that I talked about, compute-in-memory architecture. We also did that in a spiking neural network architecture, where both the MVM computations, or the accumulation, and the update of the membrane potentials are done in memory. In both these cases, we actually end up getting a huge improvement in frames per second. We were able to achieve about 35 to 40 frames per second in these particular cases. We can do, in fact, even better, and this is only simulation results that I'm showing on the right side of it, where I can use a cross-bar-based memory using RRAMs in this particular case to do these computations, and that can give you a huge amount of improvement, but there's a catch. The catch is that we got rid of the ADCs. The ADCs was a bottleneck. So since ADCs are a bottleneck, in fact, what we wanted to do is to get rid of the ADC overhead. How did we get rid of the ADC overhead? Since the area and the energy profile are dominated by ADCs and the SIM accelerators for analog computing, what we ended up doing is we decided that, hey, we need ADCs on the left, as I'm showing here, and which are large area and energy consumption. Is it possible that I get rid of the ADC completely and use a sense amplifier? The answer is that if you just do that, you're going to have a huge penalty in terms of accuracy. So rather than doing that, what we did is we had these crossbars and then ended up using 1-bit partial sums, and then accumulated the partial sums, and then trained the architecture. So the training now not only learns the data, but also at the same time learns the partial sum quantization of our training. Okay, so these, when you do together, then then magic happens, and you find that, hey, it's possible now to replace it with a sense amplifier. I don't get a decrease in accuracy. In some cases, actually, we found that its accuracy is completely comparable with the regular ADC based architectures. And the reason that happens is because the training now uses basically the quantization aware, knows the quantization. So do quantization aware training. So learn the data and the quantization at the same time to be able to actually have really good results. And this is an example of the results that I'm showing that, depending on the array size that you have, I'm showing the accuracy of, in this particular case, CFAR10 and also ImageNet. What we found is that you can almost get back all your accuracy by using this quantization aware training. And if you do that, turns out that, you get a large improvement. These are simulation results, not an implementation in a hardware, but the simulation results that you can get a huge improvement in energy consumption while still maintaining the accuracy for these designs. For FireFlowNet and SpikeFlowNet, which are basically those, remember we talked about optical flow architectures. I'm going to show this next part, which is like some hardware-aware training for the ADC-less SIMs, showing basically it actually does a reasonably good job of training. Finally, before I end, I just wanted to say that since we talked about various going all the way from sensors to algorithms to hardware, you need modeling and simulation tools to be able to do the designs. And so we talked about SIM. In this particular case, it says IMC. IMC stands for SIM, really in-memory computing versus compute-in-memory. They're all the same, right? So you need to think about IMC-aware workloads, and that you can consider, for example, pruning, quantization. We talked a little bit about some of those, crossbar-aware training algorithms and so on. And you need to think about IMC-aware workloads. And then IMC-aware workload evaluation using, for example, a PUMA kind of architecture as an example. That can be done. But on the right side of it, you also have to think about the designs where device circuit proper models are required to be able to evaluate some of these architectures, right? RTL design, synthesis, interconnects all needs to be modeled properly. So in other words, there's a need to rethink also the tools that are there to do these kind of designs. So the parting thoughts, I really believe that hybrid sensing, hybrid networks are important. So these bioplausible networks combined with standard deep learning can be quite effective in actually achieving the right kind of accuracy, energy efficiency, and robustness. They have a good amount of potential for edge computing. I didn't get to talk a lot about the devices, but neuromimetic devices that can mimic some of these operations, neuronal and synaptic operations properly, can potentially harness this synapse and neuronal functionality and achieve large energy efficiency. At the end of it, I really strongly believe that algorithm hardware co-design, guided by biological principles, can be the pathway for next generation neural computing. I also wanted to acknowledge the group. A lot of the work that I presented are really the work done by my students. And finally, acknowledgement in terms of the funding agencies who funded this work. Thank you.